So we are considering your system that is characterized by the system transfer function h, and then we are exciting the system with an input, and then we are measuring the output. So the input is the forcing, dynamic forcing term, and the output is, for example, displacement, velocity, and acceleration. Now, this name h or FRF, just to be general, is always used when referring to the system transfer function, but sometimes you can see or you can hear different names according to what are the physical quantities that your system is relating with respect specifically with the output. So generally what we are doing, what we are naming is that the receptance is the system transfer function that is linking the input that is a force with the output that is your actual displacement. So for example, we can write this equation, your alpha, that is a function of omega, times your vector of dynamic forces F is equal to your X, okay? That is the displacement. So this alpha is a matrix that is called the receptance. Okay, and F is your loading and X is your displacement. We can also link the output velocity with the input force. In this case, we refer to the system transfer function as mobility function. Okay, in general, it is referred to y omega times your forcing term equal to, let me call x dot. It is not a clean nomenclature that I'm considering because it's a mixture between the time domain and the frequency domain nomenclature, but I use this because it is clear that I am referring to the frequency domain version of the first time derivative of the output displacement. Okay, and this is the system transfer function that is called mobility. And here, of course, we have the velocity. Finally, we are also referring to the accelerants, that is the system transfer function relating the input force with the output acceleration. Okay, and it is generally referred to the A matrix times your force that is equal to x double dot omega. Okay, so that is your accelerants. Okay, matrix. And of course, we are referring to the acceleration here. So if you have a specified output quantity in terms of displacement, let me add that here now. Or velocity or acceleration, you can name the relation between these input and output, that is your system transfer function, or in the frequency domain, frequency response function, to the specific names that we are always referring to, that is the receptance, mobility, or accelerants, according to the different quantities that we are considering. If no name are given, we are setting without any other adjective the name of the frequency response function or the transfer function, okay, just to when we are referring to system properties that is capable to transform your input into an output quantity. Because of the different outputs in terms of the displacement, velocity, and acceleration, by taking into account the Fourier transform or properties or the frequency domain properties, and just by assuming that your input is an harmonic input, okay, we have the following relation when we are moving from receptance to mobility to accelerants. Okay, and specifically we can say that we can have the amplitude of the mobility function just by multiplying the amplitude of the receptor functions times your omega. So the amplitude of each component, okay, of your so each component, let me write that here in this way just to simplify notation. Yes, each component of the mobility function could be obtained by the corresponding component of your receptor function, multiplying that by omega. Okay, and that comes straight from the harmonic relation from time to time derivation is equal to multiplying the harmonic frequency response function by omega, j omega, but because we are referring to the amplitude, j is always not considered. The phase, of course, of this, the phase of your mobility function could be derived from the phase of your receptor function just by subtracting the phase of your reception function half pi or 90 degrees. Okay. And finally, we can also derive the amplitude and the phase of the accelerants, okay, from the receptance just by multiplying the reception by negative omega square. Okay, so in this case, I'm not considering any amplitude and phase. I'm just considering the component of your whatever accelerants function, okay, just by derived from the corresponding component of your receptor function and then multiply by negative omega square. And then comes from the double time derivation in the frequency domain. Okay, so that are very easily and always easy to forget relations. Okay, but I think that are very useful to remember when dealing with real life operations in the frequency domain. We are also considering the following definitions. Okay, the apparent mass, okay, is generally defined as the ratio between the input and the output acceleration. So it is the force over the acceleration. Okay. We are also referring to the mechanical impedance as the ratio of the input force over the velocity, the output velocity. And finally, the dynamic stiffness yes, as the ratio of the actual input force divided by the displacement. Okay, always keep in mind that you can have these definitions when referring with other people or other, let's say, output from other laboratory. Finally, a last remark on the typical frequency response function. Now, as a whole, I'm not entering into what kind of frequency response function I'm referring to. I'm generally referring to the relation between whatever input and whatever output does the frequency response function. I'm not referring to a specific output. It could be either displacement, velocity, or acceleration. Okay, so the frequency response function, so the h of omega is a, once again, complex function of a real variable omega. Okay, that is our running frequencies, that is the actual frequencies. And omega uh, is always a positive quantity from 0 up to infinity. Why that? Because we already discussed that the negative side of your frequency response function is not considering, because first, we know perfectly what's happening to the negative side. There could be a symmetrical or anti-symmetrical function with respect to the positive omega axis, according to the different part of your FRF. And the contribution of this negative side FRF to the actual picoresonances, for example, is negligible. So that's the reason why we are not considering that when we are analyzing your system response. However, when you are considering the anti-Fourier transformation, that is when you want to go back in time domain from the information that you got in the frequency domain, then you have to take into account also the negative frequency side. So you have to resynthesize your two-side FRF in order to have the full synthesis in the time domain of your impulse response function. But however, now when we are referring to h as a general frequency response function, we have to consider that it is a complex function of a real variable omega, and therefore we have to represent these complex functions by using at least two information. Okay, that means that we have to consider different type of representation, or if you want, graphical representation or function analysis. And these are, the first one is the amplitude versus the frequency, and the phase versus frequency. Okay, the second representation, B, is the real versus frequency, or the imaginary part versus frequency. The third way of representing your FRF is the real part versus imaginary part, in which, remember, the frequency is a parameter. Okay, so just to stick with what you should already know, this first representation, the amplitude versus frequencies and the phase versus frequency, is what we already seen, hopefully, as the body plot. Okay, whereas the last one, the real versus imaginary, having the frequency as a parameter, sorry, is the Nyquist representation. Okay, and typically what we are having, okay, is that when you are referring to the frequency response function, okay, what you are having is that you need both of the two representations, okay, and that could be either the amplitude and phase or real imaginary, generally speaking. And typically what we got here is just making a plot, very easy plot, okay. in which I have in the y-axis the omega, the running frequencies, and in the x-axis, for example, I can have um, the amplitude of your FRF, something like this, okay? And then we are having plots of this shape. We're referring to the amplitude, okay? Or we're referring to the phase, always as a function of your running frequency omega. We are having something like this. Okay, in which there is a specific condition here at a specific frequency that is called natural frequency, as you should know, in which we have the maximum of the amplitude of your FRF, and we have what is called the quadrature condition of your phase. Quadrature condition because your phase angle, okay, is a quantity that is going from 0 up to negative pi, passing through the quadrature condition, negative half pi. I am referring here to the receptance, that is the relation between, for example, the displacement, output displacement, and the input loading force. What does it mean that? Please be sure to have this picture very clear in mind, because it could happen that I will ask you to draw during your final exam picture representing your whatever frequency response function. And sometimes there are lots of big mistakes in representing this function. So please note that here, when omega is 0 or practically 0, the frequency, the amplitude of the frequency response function here, okay, is your flexibility. Okay, so remember, we are referring to the fact that your frequency response function is the inverse, okay, of the dynamic stiffness. Okay, so that is representative of the dynamic of the static flexibility here. Okay, when omega is equal to 0. Okay, it is 1 over k specifically. Here, when we are assuming, and that is how we have to understand this picture, when we are assuming that the system is excited by an harmonic excitation having a unitary amplitude and a frequency omega, whatever it will be, this plot is telling me what is the amplitude of the response to this unitary excitation for different omegas. Okay, so what is happening here is that if we choose one omega, for example, the one here, we are having that the amplitude of the response is a little bit higher with respect to the amplitude of the response when I am exciting that structure with a harmonic excitation characterized by a 0 frequency of the harmonic. That is a static force. Why that? Because it starts playing a very interesting game. The two forces, the inertia and the elastic reaction of the system, so that the output response is start having a higher amplitude than expected from the static behavior. And this amplitude is going higher and higher as the frequency is approaching the natural frequency of the system. Okay, sorry, I use Fn. Maybe we can use omega n to be consistent with the axis. Sorry for that. Omega n, omega n. Okay, when we are having the excitation of your input, the harmonic excitation of your input forces with an excitation frequency equal to the natural frequency, then the amplitude will be maximum. And as we already saw last class, yesterday class, the response is driven mainly by the damping ratio. If the damping is 0, then your amplitude will go to infinity values, okay? And as we are passing this frequency, or in other words, as the frequency of the unitary input excitation is higher than the natural frequency of the system, then the response is getting lower and lower until when we are exciting the system with very large frequency, the system, or better the inertia, made the system not to be so responsive to the input excitation. And indeed, as you can see from that picture, we are having an output response that is less than the input, then less than the output response at omega equal to 0. There is an attenuation. That's because the system can't follow the high frequency harmonic excitation when the frequency is very large compared with the natural frequency of the system. And therefore, here too, when we are considering the large frequency, there is a very large attenuation. Okay. What is the meaning of the phase of your FRF? The meaning of the phase of the FRF could be understood just by recalling the same example. I am considering the system excited by a unitary amplitude external excitation having a frequency that is changing from 0 up to infinity. When we are having an input excitation with 0 frequency, it means very easily that you are exciting the system with a static load, and therefore there is no phase delay, or in other words, the system response is synchronous, perfectly synchronous with your input excitation, with your forcing, okay? And that's the reason why the phase angle is practically 0, and is practically 0 when omega is a little bit higher than 0, but however, very small compared to the natural frequency. As soon as the frequency becomes greater and is approaching the natural frequency, what we can see is that we are having a phase that is the response of the system is going to be in, let's say, in a sense that you are not more extracting energy as the system is excited by a frequency that is crossing the omega n. And when we are at the natural frequency, the system response and the input excitation are somewhat, let's say, orthogonal. There is no interaction. The energy is not passing through the way that we are used to have, okay, because the system is putting all the input energy, okay, into the damping. So all the input energy is dumped out, and there is no more interaction, sort of interaction between the input excitation and the output response. And that is the specific condition that we are referring to as the quadrature condition, in which the input and the output are orthogonal one each other. There is no interaction at all. But as soon as the frequency of the unitary excitation is getting higher than the natural frequency, as we can see, there is a delay, a further delay of your response with respect to your input. And that means that there is an out of phase response with respect to the input when omega is getting very high. That is getting values that are going to an infinite. And here we are in the opposition conditions. That is, the phase angle is pi, sorry, and therefore it is characterized by mainly a change of sign when you are considering an input excitation with very high frequency of excitation with respect to the natural frequency. Okay, so this is a very uh, easy way of thinking at the frequency response function, and in terms of amplitude and phase. We can have the same representation, we can have the same analysis as we had with this amplitude and phase when referring to the real and imaginary part. Okay, when referring to that, the typical plots are the one that I'm now going to draw. Let me, oh, sorry, let me consider here your omega, your real part of your FRF, H, okay? And once again, the typical plot is something like this. Oh, I like to stay. Okay. And the imaginary part could be something like this. Okay, as we can see, the real part of your FRF is crossing the zero axis when the frequency of excitation is once again equal to the natural frequency of your system. Okay, when omega is equal to zero, we have the flexibility once again, because the real part is the only uh, part, non-zero part to the FRF, whereas the imaginary part is zero. Then when we are the crossing of the x-axis, the natural frequency, it is clear here that the system is reacting with an imaginary contribution only, and that is once again an evidence of the quadrature condition. The response is purely imaginary. It is rotated at a half pi angle with respect to the input. Okay, they are orthogonal. Output and input are orthogonal. And then when we are referring to the behavior of the frequency response function, when omega is going to have infinity value, very large values, then the response is always zero, both with respect to the real and with respect to the imaginary part, as we can see from this picture. And once again, the system is not capable at those high frequency to follow the system, the system input at those large frequencies. Okay. But however, please review this. I know that you already saw these pictures, saw these interpretation in other courses. Please review all of them and be very familiar with that, because that will be our, let's say, typical plots that we have to consider from this part of course to the end. Okay, so it is very helpful for you to have a command of these plots and this mean. Of course, when you are considering now, I am just showing you the amplitude and phase part of your frequency function. If you are having more than one natural frequency, that is, if your system is having more than 1 degrees of freedom, then of course you have to introduce the other peak of resonances that are happening at different values of the x-axis, and therefore you will have more than one peak and more than one quadrature condition that you can have here when reporting the phase. And also when we are referring to the real and imaginary part, then we can have additional crossing of the x-axis, both with respect to the real and imaginary part corresponding to the different natural frequency. And once again, we will have a local minimum or maximum of the imaginary part corresponding to zero crossing of the real part of your FRF. And those conditions are happening at the frequency that is equal to one natural frequency of the system. Please note that this response, once again, is the meaning of this response is the response of from a unitary harmonic excitation, a unitary amplitude harmonic excitation having that running the value of frequency of excitation equal to the actual value of the omega. Now, having said that, I want to discuss a little bit what are what is the usefulness of these evaluation. The usefulness of this evaluation could be viewed here from the very beginning of this today's class. Okay, here. Okay, we have a very rough representation of your system characterized by H and then an input and an output. As we already discussed about, when dealing with your whatever numerical model, your space model, that is the mass, stiffness, and even damping distribution, could be represented, for example, as a mass, stiffness, and damping matrix in a finite element model, for example. And using that, you can easily solve the eigenvalue problem associated to this space model. Okay, and if you're using, for example, the finite element code, the commercial finite element code, MSc Nastran or ANSYS, it is very easy to solve for this problem, for the eigenvalue problem. Therefore, you are evaluating the model parameters of your system. But when you are dealing with your experimental activities, when you are dealing with the experimental structural dynamics, then what you are having is just the capability to excite the structure and to measure the output. So the only way to characterize your system from the experimental point of view is just the evaluation of the frequency response function. So from the experimental point of view, the response model is the first representation of your system properties just from the measurement of the output corresponding to a specific input. And you already have the tools to identify these frequencies of functions because you already saw how to excite the structure and how to estimate your FRF from the output and input measurements. I'm just referring to the H1 or H2 estimators, for example. Okay, and therefore they are passed to the power spectral density properties. Okay, so it is very important to have your response model, and now to link this response model to the modal model in order to start the estimate of the model parameters. And indeed, this last part of the class is dealing with the modal parameter identification, or better, the modal parameter, the estimate, sorry, of the modal parameter. Okay. So once again, we are very happy because we have the structure. We went down in the laboratory and we excite the structure. We measure the input excitation and we also measure the corresponding output response. And by using the estimating method, for example, H1, H2, we are able to obtain your response model. So what I can write here is that the response model that is your H of omega, remember, is a complex quantity of a real variable omega, okay, is experimentally identify from the measurement of both the input loading and the output response. Okay, and that is your starting point. Okay, and generally we can add H1, oh sorry, H1 or H2 estimators are used. Okay, then in the experimental world, model parameters are identified from these estimates, okay, from this H1 or H2, that is from the response model. So the experimental model parameters are estimated from the response model that we have just identified. Please note, I emphasize the estimated word, okay? Why that? Because on the we have to estimate. We are not simply calculating, evaluating from from a numerical subroutine these model parameters, because an estimation process is always required, because the solution to this problem is not a unique one. It is a sort of, let's say, generally speaking, the solution of a minimization process. Okay, and so we have to find the best, sorry, best solution for the given uh, estimated FRFs. Okay, we will see this later on, so we will enter into more details into this estimation process. But however, please remember, when referring to the experimental model parameters, we are not allowed formally to talk about evaluation, but estimation process, because once again we have to estimate and not just a pressing button is enough to press button is enough to estimate your model parameters. And a simple justification of that could be derived when referring to your relation between the response model and the modal model. When referring to, once again, to your whatever system that is excited by an input excitation, okay, with the degree of freedom J omega, and then we are having an output X at the degree of freedom I, that is always referring to omega, and therefore we are considering this frequency response function that is related to the output I and the input J of your whatever system. We can refer to this relation between the response model and the input, the modal model, okay, in this way. Um, Let me write this as a summation sign from R that is going from 1 to infinity, because the system has infinity degrees of freedom, okay, and then this we have the residual terms that we already saw, AJR divided by omega and r square negative omega square plus j eta r omega n r square. Okay. And because we are in a discrete world, I have to add a subscript L, okay, to the actual value of the frequency line omega. So everything should be referred to the L index. Okay. Please note that I am considering the damping factor eta, okay, instead of the more common damping coefficients zeta, okay. But we can say that at the natural frequency, okay, we can say that the j omega n r square, sorry, omega n r square eta r is equal to 2j omega n r theta r, okay. And as you should know, okay, the damping factor theta r is equal to 2 theta r omega L over omega n r, okay, when omega r, the actual running frequency, is equal to the natural frequency of the system, then what we can say is that the damping ratio is just equal twice the damping coefficient. Okay, so this is brief remark of the usage of these two um, expression representations of the damping mechanism. Okay, but however, having said this, so we can write this modal both in terms of the damping factor and in terms of the damping ratio. Okay, but the most important thing is that we can review that frequency response function, okay, as a further summation of three main contributions. So let me write that as a summation from the index r that is going from 1 to, let's say, m1 negative 1, okay, all the previous quantities plus the summation sign from r that is going from m1 to m2, okay, all the previous quantities plus the summation sign from the index r that goes from m2 plus 1 up to infinity, and then we are considering all the previous quantities. Okay, let me call this, okay, the quantity star, okay, and that is what I'm writing here, okay, just to be short in writing. Okay, so having said that, what I just tried to write is that my summation sign that is just telling me that the dynamic behavior of your system at whatever frequency is the composition of all the modal contributions that we consider as the Seidel fraction expansion, like the one that we are used to have in terms of residual terms, the numerator, and the poles of the system, the denominator, okay? But instead of having all these terms that are running there all together, we distinguish the terms that are in the frequency range that we are analyzing with respect to the other that are out of our frequency range. Specifically, I am assuming here that my modes of interest are from mode index M1 to mode index M2, whatever they are. They could be the first one, the 10th one, doesn't matter. And the summation sign that goes from the first one to the M1 negative 1 means that I am considering all the modal contributions that are acting at a frequencies less than the first frequency that is composing my frequency range. And the last term of this summation, okay, that is my summation sign that goes from M2 plus 1 to infinity, okay, is just taking into consideration all the higher frequency modes with respect to my frequency range of interest. So here I am having all the modes included in the frequency range of interest. Here we are having all the modes below the frequency range of interest, and there what we are having all the modes higher than the frequency range of interest. Okay. And of course, the summation side could be, especially the first one, that they are including all the modes below the frequency range of interest. Maybe it could be an empty set, I don't know. But however, we have to include all of these things. So if you want, we can have a representation of this triple summation sign with this plot. So let me write this whatever frequency response function. So I'm considering the amplitude of your whatever frequency response function. Okay, that could be written like this. For example, and let's assume that my frequency range is the one that is, for example, going from this value and these other values, so initial and final. Okay, so these, as you can see, this plot could be reviewed as this contribution, okay, and so far and so on, okay, like this. We are referring to the typical Sievex expansion, okay, of your whatever system response function, okay. So what we can say is that your in your frequency range here, that is lower than your initial frequency range of your frequency range of interest, okay, the contribution of the whatever Rth modes And for example, the R mode could be this one, R, R+1, and so on. Okay, okay. To the FRF, to the frequency response function, is practically constant. We already discussed that. Okay. Whereas the contribution of modes that are at higher frequency, with respect to your natural frequency R, is constant. Okay, let me write that better. Constant. And these contributions are called upper residuals. Okay, upper residuals because they are the contribution, once again, of the modes that are acting at higher frequency with respect to what we are considering, to the, for example, the NF, for example, the initial one. Okay, oh, not the, sorry, yeah, to the initial one. Okay, and this contribution of the upper residual, okay, is of the shape 1 over Kij region. Okay, that is your flexibility that we already discussed. For frequency, we're referring to frequency that are larger than what I call the final, okay, omega final, that is telling you what is your frequency range of interest. Then the contribution of the R mode, okay, to the same FRF is this time practically the mass line that we discussed yesterday. Okay, so is proportional this side to negative 1 over omega L, the mass corresponding to degrees of freedom that we are considered in a rigid way. Okay, if we are having proportional damping, just to have a model. Otherwise, it is something related to the mass line characterizing the dynamic mass of that part of the frequency construction. Okay, and so what we can say is that the contribution of modes that are acting at lower frequencies, okay, with respect to your omega that is setting you the frequency range of interest, is proportional to the mass line. Okay, so it's 1 over omega L square, I forgot square there and here, MIJ R. Okay, and these are called the lower residual. So we can say that as the lower residual terms. And there are we are upper residual terms. Okay, so as a matter of fact, what we can say is that your frequency response function, once again, Hij, that are referring to a couple of input and output, evaluated at the L frequency line could be written as the upper residuals plus the contribution of all the modes that are in your frequency range of interest, that is from M1 to M2, okay, AIJR divided by omega n r square negative omega L square plus J eta R omega n R square plus the lower contributions, the lower residual contribution that is contributing to the actual from that are contributing from the higher modes to the frequency range of it. Okay. Let's stop for 5 minutes. Okay, we will resume our class, let's say, at 3:20. Any questions? Any questions? Okay. Let's have your break.
Professore, scusi. Professore?
Sì, dimmi.
Senta, volevo una domanda, ma il fatto che diciamo che ad alte frequenze diciamo, la risposta è solamente influenzata dalla massa, sarebbe a dire che cioè, come se ad alte frequenze cioè, il sistema non riesce a rispondere con la rigidezza, quindi l'unica risposta è quella inerziale. Può essere un'interpretazione.
Sì, in certo senso sì.
Ok.
The question from your colleague, let me translate that first.
Sì.
So the question from your colleague is that the mass line contribution, okay, that is here, is due to the fact that at higher frequency, the inertia is not allowing the system to follow the input excitation for those higher frequency. Okay, so that's the reason why the behavior of your frequency response function at higher frequency is proportional to that term that I introduced here. Okay, and these we call that lower residual because it is the representation of all what's happening at lower frequencies with respect to the actual frequencies. Okay, and that is typical of the mass line. Then another question.
No, sì, era questo qui la cosa, professore. Grazie.
Okay. Prego.
Can you scroll up to the very beginning? I just missed a few of your notes.
Higher on top?
Yeah, like the beginning. When the class first started. Okay, okay, you can go a little bit down. The next section. Stop here for a second. You can stop.
Body, not body. Body plot. Down?
No, that's good. That's good. Thank you.
Okay, so let's get started. We have a few minutes break. So that is your relation that is practically used in experimental structural dynamics to estimate your model parameters from the estimation of the frequency response function that is your first physical quantity that you can have from the measurements of both the output and the input of your system. So the unknowns, what we just discussed, the unknowns sorry, in the model parameter identification process are, of course, the residuals, so A, I, J, R, the natural frequencies, okay, the damping ratio or the damping factor R, and then the lower residual and the upper residual. Okay, please note that all of these, okay, are for all the index R that is ranging from M1 up to M2. And please note that your model parameters in terms of most shapes, okay, the numerical I component of mode R and the R modal masses are in the residual term, okay, R, okay. That is, what we are having are much more equations, okay, than the unknowns. Okay, in general, of course. Why that? Because you know your frequency response functions, okay, Hij, are all the frequency lines that are available in your experimental analysis. And if you remember, your experimental analysis will involve the fast Fourier transform, will involve the time to frequency domain transformation. And in this sense, the number of frequency line is always a power of 2, in which the exponent is easily 10, 11, 12, 13, 14. So 2000, 4000, 8000, okay, frequency lines. And that is the reason why the number of unknowns here are, of course, less than the number of equations, that is the number of frequency lines that we can have. And thus, we have a curve fitting procedure that is required to estimate your model parameters, okay? So what is called a curve fitting approach is used. Okay, to estimate the model parameters. Okay, so that's the reason why I start talking about the model parameter estimation process by referring to an estimation process itself, because we are not just solving a problem, but you have to estimate, you have to put your human being decision, opinion on what will be your model parameter. We will see that how it will be in practical uses. But for by now, just let's consider that because we are referring to a process that requires, that is characterized better by a large number of equations than unknowns, we are referring to a curve fitting, or we are referring to an estimation process of your model parameters. Why that? Please remember the starting point is this such equation that I would like to highlight better. Okay, like this. Okay, that is your starting point. In the estimate of model parameters. Okay, and here we have all the ingredients, the model parameters itself, that is the mode shapes and the model masses are all in the residual terms. We are having the RAIJ residual terms. Please, we have three indexes. The right indexes are generally referring to the pairs of input and output points, whereas the left index R is referring to the half model contribution to that frequency line. And then the denominator, that is your giving you the pole of the system in terms of natural frequency, omega and R, and the damping ratio or the damping factor, eta or zeta. Okay, so we have to solve for those unknowns. There are lots of estimating process, okay, and this estimating process, okay, could be grouped according to the domain and the model that are using. Okay, so sorry, okay. Several exist to estimate the model parameters. Okay, and they differ one each other according to the model that they are using and the domain that we are considering. Specifically, what we got is a sort of this, let's say, matrix view of those approaches. Okay, like this. We are considering the single degree of freedom method and multi-degree of freedom method. Okay, these are referring to your model that we are considering, model, and then we are having time or frequency domain. Okay, so here we have at least four approaches that we can consider, and indeed we will start doing that. Okay, so let's start with the one of the first approach that we we had in literature, and this approach is a single degree of freedom model and is based on the frequency domain representation of your system response function. Okay, so the first approach that we are considering is the one that is called half power bandwidth method. Or the peak peaking method. Two names for the same approach. Okay, what are the hypotheses of this approach? The hypothesis is that the system is behaving as a single degree of freedom system, okay, around the natural frequency omega n, for example. Okay, please note that it doesn't mean that the system is just having 1 degree of freedom as the Lagrangian coordinate. Okay, we can have a multi-degree of freedom system as a discrete representation using Lagrangian coordinates of your system. However, when referring to your system transfer function, when you are referring to the frequency response function, what is we are assuming within this half power bandwidth method is that the system is practically behaving as it were a single degree of freedom around the natural frequency, as it were an harmonic oscillator just around the natural frequencies. And therefore, we can review the overall system as the composition of several harmonic oscillators, each one located at each natural frequency. Okay, so we are assuming that the system is behaving as a single degree of freedom system around the natural frequency. Full stop. Not in the space domain, just in the modal domain. Okay, and of course we are assuming that we are acting in the frequency domain. Okay, just to refer to the previous table. Okay, so when this hypothesis is a good one, we are assuming that this hypothesis is an acceptable when the modes are well separated, okay, and when low damping, okay, is characterizing your modal behavior, okay, low damp modes. Okay. Furthermore, we are assuming that damping, zeta generally speaking, damping should not be too low, okay, because we need to estimate, we need the estimate of the omega n, and of course if the damping is very low, then the system response could vary a lot across the natural frequencies. Therefore, from the experimental point of view, we can have issues in finding the natural frequency, okay? And of course, damping should not be too high to avoid mode coupling. Okay, and therefore that's the reason why we are using better this approach when we are in a condition for which all modes are distinguishable one each other. The damping is not that high. By the way, not that high means that we are accepting a damping ratio of about some percent, okay, as we used to, and the natural frequencies are well separated. That is, we can identify all the peak resonances when looking at the whatever frequency response function of your system. Okay. Of course, there are also many other techniques that are characterized by higher accuracy than this approach, but this is the basic one, and it is also very useful for, let's say, on-the-fly estimate of your model parameters. So, let's start with your...
Professore,
Sì?
potete ripetere perché il dumping non deve essere troppo basso?
The damping, the question is why damping should not be that too low. The answer to this question is just by referring, could be obtained just by referring the behavior of your FRF across the natural frequencies with zero damping or very low damping. In those cases, what you're having is that the amplitude of the responses is varying a lot just by having small changes with respect to the natural frequency. For example, you can have an infinite value if there is zero damping when you are at the natural frequency, and a finite value when you are a little bit out of this natural frequency. So this very high sensitivity of the frequency response function value with respect to the value of the natural frequency could be could affect a lot the estimate from the experimental point of view. Remember, we are not having a continuous function, we are having a discrete function. So when we are having a very high variation of your response with the change of the frequency, then we can have some issues in estimating the peak of resonance because the damp is very low.
Ok, grazie.
Okay, so now let's see from the model point of view what this single degree of freedom hypothesis is leading us. Okay, where? So the Hij of omega, whatever it will be, could be rewritten as a summation from R that goes to 1 to number of modes. Now I'm just considering that the lower and upper residuals are not there, so I am shifting the indexes of the summation side, the index of the summation side from 1 to the number of modes that are of interest in our analysis. The residual term could be explicitly written as your psi R mode component I times your R mode component J, and then your R mass times, let's introduce, it doesn't matter, once again, the damping ratio as your omega and R square, R's natural frequency, negative omega square, plus 2J omega and R, and then damping ratio theta R. Okay. Now, with the hypothesis of single degree of freedom in the model domain, we can rewrite that as Hij, that is referring to the pth natural frequencies, okay? Pth natural frequency. This could be rewritten as phi I of the p mode, phi j of the same p mode, divided by 2j omega and p square theta corresponding to the pi mode. Okay, please know that I consider normalized modes now. Okay, and here viscous damping model, just to be sure. So what is the effect of this single degree of freedom hypothesis? The effect is that we are having only one term is characterizing your H, okay, around the considered pth natural frequency, of course, and that is a big advantage, as we can see later on. Now, let me go and describe your peak peaking method. The peak peaking method is considering three phases. Okay. So peak peaking method. Oh, let me change. So peak peaking, three steps. So the first one is the estimate of the natural frequency. The second one is the estimate of the damping ratio, corresponding to the natural frequency. Okay. I don't like this. Okay, P and P. And the third step is the estimate of the eigenvector, the pth eigenvector. Okay, so let's go describing these three steps. First one, estimate of the natural frequency, whatever it be. I'm forgetting the p index. Okay, so how can we do that? We just have to check that the frequency response function at the natural frequency is characterized by the peak of resonance and the quadrature condition when referring to the amplitude and phase representation of the frequency function, or, but that's the same, we have to check that the real part of the frequency response function is crossing your omega axis, corresponding to a local maximum or minimum of your imaginary part. Okay, so we can say that the natural frequency is estimated from, okay, straight from the FRF. How? Let me write this and drawing this plot. It should help you in doing this. So this is the amplitude with respect to the frequencies. Then what we got here, for example, is a plot like this. Let's assume that this is what you got from the experimental analysis. Okay. And if we are having not only the amplitude, but also the phase of your FRF, what you got here is, for example, this. So something like that. Okay, so we got 0, negative pi, negative 2 pi. Okay, and these are the quadrature condition P4. Okay, and this is the other one corresponding. Okay, so what we are having here is your natural frequency omega and p. We got here omega and p plus 1. If we are having, so the natural frequency omega and p is at omega where the amplitude is maximum and the phase of your omega is in quadrature. Okay, so that is what you have to check. For example, here the natural frequency is the one corresponding to the peak of your FRF. We have a quadrature condition here. We have another quadrature condition there. Okay, as you can see, and therefore we have found the natural frequency. When we are dealing with the real and imaginary part, we have to follow the same approach. So let me consider the same plot in which we are reporting as a function of omega the frequency response function, but this time the real part of h. Okay, and as we already discussed, the behavior should be this one, for example. For example, like this. Okay, the corresponding imaginary part could be, let's say, when plotting that, okay, could be something of this shape, for example, this. Okay, so here once again we are having the natural frequency p, and here we are having the natural frequency p plus 1. Okay, if when the real part of the frequency response function is crossing the omega axis corresponding to a minimum or a maximum of your imaginary part function. Okay, we got the local minimum in this case, and we got the local maximum, okay, of your imaginary representation of the frequency response function corresponding to this zero crossing of the real part. So the first step is the estimate of your natural frequency that is done just simply referring to our dynamic model. We know very well that the FRF is behaving as characterized, by a maximum and a quadrature condition at the natural frequency. So you have to experimentally check just by looking at your just estimated frequency response function using H1 and H2 estimator, okay, or both in terms of amplitude and phase, or in terms of real and imaginary part. So omega, in this case, for example, last case, your omega and P is corresponding at the frequency where the real part of your H omega is equal to 0 when the imaginary part of H omega is maximum or minimum. Should consider as a local value of the maximum or minimum. Okay, so that is the first step. Questions on this? Now, if no questions, let's go to the second step, that is the estimate of your damping ratio. Okay. Second step, estimate of the damping ratio. In order to estimate the damping ratio, we have to refer to some analytical details. Okay. In order to do that, let me consider to evaluate the average power that is dissipated in a period from the viscous force, okay, that is characterizing your damping, okay, when we are exciting the structure with harmonic excitation, okay. So let's evaluate the average power dissipated by the viscous force in a period, okay, when the system is excited by a harmonic loading of the shape Ft, okay, is equal to your amplitude, that is, for example, F0, times a sinusoidal wave of a frequency omega. Okay. What is first the response? The resulting harmonic response is thus your xt. It is given you by the amplitude that is sort of filtered by your system FRF amplitude times your sinusoidal wave that now is including a sort of phase angle. Okay, we can write that because the input is harmonic one, and the velocity, the corresponding velocity, is just the time derivative of the previous one. Because we are in harmonic conditions, it is also very easy, just a matter of multiplying that by omega and change the sign with cosine. So it is equal to F0 of omega, then the effect of the FRF at that frequency, and then cosine omega t plus the phase angle. Okay, now remember the h, okay, is equal to, could be written as 1 over k. K is the stiffness, equivalent stiffness in a single degree of freedom system, divided by 1 negative omega and the natural frequency square plus j2 omega and theta. Okay, that is a single degree freedom system, so that the amplitude of your system square is equal to 1 over k square divided by 1 negative omega over omega n square plus 4 theta n square and then omega over omega n square. Okay, and so go back to the information, to the question, the first question: what is the average power that the system can dissipate when excited by harmonic excitation? Okay, so the average power, so the average in a period is given you by the integral over all the period, okay, of your Cx dot, okay, times x dot. Okay, this is the dissipating force, and that is the velocity. Okay, and we have to take the average over the whole period. We can write that in several ways. Remember, C, okay, could be referred to the damping ratio as C over the critical damping, okay, and that is equal to 1/2 critical damping times omega square, the amplitude of the force in turn square, divided by the stiffness square, and then we got this ratio theta n divided by 1 negative omega over omega n square, everything square, okay, plus 4 theta n square, and then omega n square. Okay, that is the average. Now the question is because this average power, as you can see, depends on the frequency omega. By varying the omega, you have different average powers. Okay, the question now is there a value of this running frequency omega to which correspond an average power that is maximum? The question could be answered just by solving for this equation. The maximum average power, okay, is given by solving this GP average, that is a function of omega, with respect to omega, okay, and then we have to set this equal to 0, okay. What we found out is that the maximum, so as a result, the maximum average power is dissipated at omega equal to 1 natural frequency of the system, and the maximum average power is equal to 1/8 critical coefficient, damping, times omega n square, F0 squared is the amplitude of the input force, divided by zeta n, and then K square. Okay. Having said that, let us now evaluate the condition, the value of the omega, for which this average power is half of the maximum that could be dissipated. Okay, the condition for which the average is given, okay, when, just by looking to the previous equation, when 1 negative omega over omega n square negative 4 zeta n square omega over omega n square, okay, is equal to 0. And the solution of that is omega over omega n 1, 2.
I don't think the board is capturing what you're writing.
Say again, please.
I don't think the board is capturing what you're writing.
Okay, let me see. No, it seems not. So let me do that again. Okay, now we got it. So the solution to that equation is are four value of this omega. The first two are given by this equation, negative zeta n plus minus root square 1 plus zeta n square. The other two are omega con n 3 and 4 that are even, plus zeta n plus minus root square 1 plus zeta n square. By taking just the physical values of this natural frequency of this solution, okay, what we can have is that the physical are just two. And these are omega over omega n 1, 2, I take every number of that, are negative plus theta n plus plus square 1 plus theta n square. Because of that, we can say that, and this is first step, first finding, that the theta n, that is the damping ratio, could be simply evaluated by this very nice formula. And of course, we can also have omega n square equal to omega 1 times omega 2. Okay, so this is telling us what are the how we can estimate the natural frequency, the damping ratio from the variation of the frequency omega 1 and 2, to which correspond half of the power that could be dissipated by your system when excited with an harmonic excitation, with harmonic loading. Okay, if we know those half power frequencies, omega 2 and omega 1, then it is very easy to find out the corresponding damping ratio, because the damping ratio is simply given you by that very nice formula, omega 2 negative omega 1 divided by 2 omega n. So the problem now is finding out the omega 2 and omega 1. This is the problem of the Friday class. So please, I'm asking you not to cry because I'm not giving you this information right now. Please hold on, and I will tell you the final of this story this Friday. Okay, so just 3 days apart, so you can wait for that. Okay, so that's it for today.
Io non vedo la lavagna, scusi.
Vede? Can you see that?
E dopo just non leggo più niente.
È un problema tuo, però.
Ok.
Non so.
Sto provando a rifare, a rientrare, eccetera, però, ma continuo a non vederlo, quindi non so se...
Can you all see the screen moving? Is the screen updated?
Yes, Professor.
Okay,
so it is just supposed to. I'm trying now to logging out and logging in just to make sure that you can see that. For a very few seconds. Okay, I'm now going sharing screen. Okay. Can you see it?
Sì, adesso sì, grazie professore.
Okay. However, you have the hard copy or the digital hard copy saved for you, so don't worry. Any other question? Okay, if there are no questions, thank you very much to all, and see you on Friday. Please, on Friday, we will have your laboratory activity number 3, okay? We will do that together.
Vederci.
Thank you, bye.